While radar is indispensable, it does not always indicate a tornado. Trained spotters can. Spotters tracked this tornado from start to finish, while radar never showed it. Spotters, they are the most reliable source of information we have about tornadoes.
This film is about how to identify tornadoes and how to recognize the cloud structures that produce tornadoes. Virtually all tornadoes come from thunderstorms, and thunderstorms start with cumulus clouds like these. The process is speeded up in this time-lapse film. Thunderstorms start when warm, moist air becomes buoyant and begins to rise. This air expands, cools, and condenses to form clouds. The cloud towers you see here are updrafts of rising air. You can see these updrafts grow to higher altitudes as they build in columns several miles in diameter and over 10 miles high. These towering clouds have now developed into a thunderstorm, which might bring heavy rain, hail, strong straight winds, and possibly tornadoes. Here is a representation of an entire thunderstorm to help you pick out that part of the storm that is most likely to produce a tornado. We are looking northwest. These sharply outlined and rapidly ascending towers locate the storm's most intense updrafts. The storm has reached its peak altitude and is being blown downstream into an anvil by high winds aloft. The cloud base under these towers is generally free of rain. Most of the precipitation falls out here, to the north and east of the rapidly building tower. The tornado will most likely develop underneath these towers to the southwest of the main precipitation area. Large hailstones often fall immediately to the north and east of the tornado. The tornado usually comes out of a cloud formation called a wall cloud. You may see rotation in the wall cloud prior to the tornado. This thunderstorm, seen from about 30 miles away, draws air from miles around into its updraft. A tornado would come out of this part of the storm directly below the building towers. The rain and hail fall here to the northeast. Another storm, speeded up again. This one is about 10 miles away. Time lapse again. This approaching storm is even closer. Notice the absence of rain below cloud base and the updrafts above. Now we're looking under the cloud base. It's dark here because there's a 10-mile thickness of cloud above. You are looking west. Looking west again, at the right, to the north, rain. At the left, a rain-free cloud base at the southwest edge of the storm. This is the part of the storm where tornadoes are most likely to form. Most tornadoes come out of the formation you see here, the wall cloud. The wall cloud is an isolated lowering of the cloud base. It marks an area of strong updraft and should be watched carefully. It may produce a tornado. Even without a tornado, winds beneath the wall cloud may be extreme. Large hail may fall from beneath or near the wall cloud. Here, to the right of the wall cloud, is heavy rain. From a distance, you can see vertical cloud towers rising above the wall cloud. Looking west, rain to the north, rain-free base to the south, wall cloud silhouetted against the sky. Wall clouds can take on different shapes and forms. They are typically 1 to 3 miles in diameter. They're always connected to the cloud base, usually just outside the rain at the southwest edge of the storm. When you can see the wall cloud rotate, it's dangerous. As the updraft draws air into the wall cloud, the air begins to rotate. As the air approaches the center, it spins faster. The motion is like the whirlpool in a bathtub drain, upside down. Sometimes you can actually see the spiraling motion in the clouds. Here's where the tornado is forming. A tornado is a violently rotating column of air in contact with the ground. Rotation is happening on a broad scale, and the tornado is an outgrowth of the rotation. Look at the rotation in this wall cloud and in the small detached clouds below it. Most tornadoes move from the southwest at average forward speeds of 30 miles per hour. Speeds have been clocked up to 70 miles per hour. Here's Cabot, Arkansas. This unique time-lapse sequence of a storm shows all the elements that produce tornadoes. Updraft, rotation, and, below the base, a wall cloud. Out of this wall cloud forms a tornado. Sometimes you might not see the funnel at all, especially when it is nearly overhead. However, there might already be a tornado, even though the funnel is not yet visible. The cloud of whirling dust and debris might be the first sign that a tornado is forming. There's a connection between the funnel and the debris cloud on the ground, even though you can't see it. The debris cloud here is unmistakable. This tornado is an entire column of dust. Dust, however, can make spotting difficult, especially at a distance. Look close. Lindsborg, Kansas, September 1973. What you see in the distance is obscured by the hill. It looks like a cloud on the ground. It is a cloud, a wall cloud. As it approaches from the southwest, a giant tornado reveals itself. It's making a damage path half a mile wide. 30 minutes later, the same storm strikes Salina. Here, the tornado shrinks to a slender rope-like filament, yet it is still destructive. Look at the debris cloud. This monstrous tornado was half a mile wide at the ground. Imagine this tornado with trees and hills in the foreground. It might be very difficult to identify. It's difficult to spot a tornado at night. You may hear the sound of a tornado at close range. Remember, if you're in large hail, the most dangerous part of the storm is very near. Sometimes lightning can illuminate cloud features, such as this wall cloud. This tornado over Tulsa shows you a clue for night spotting. Look for flashes of light when the tornado hits electrical power lines. Tornadoes in the southern states are often hard to spot because they are embedded in heavy rain. Tornadoes in the south may resemble this one, where low clouds, rain, and trees hinder the spotter. A tornado can split into several smaller tornadoes, then later rejoin into one. Here's the Xenia, Ohio tornado of 1974. This wall cloud over Oshkosh, Wisconsin, produced a multiple vortex tornado that was incredible. These are mammatus clouds. Mammatus are high-level clouds that can be seen on the underside of the anvil. They are not dangerous. Remember the structure of a storm. When a thunderstorm approaches, the first cloud feature that might catch your attention is the shelf cloud. The dark background behind the row of clouds is rain. In fact, it is the rain that cools the air and creates the outrush of wind called the gust front at the leading edge of the storm. Behind the gust front are straight line winds that may gust to more than 50 miles per hour. This rain-cooled air may create another type of cloud along the gust front called a roll cloud. This horizontal cloud is not a tornado. It is unusual for a tornado to come out of the leading edge of the storm. Now we are back near the southwest edge of the storm, looking west, where you would expect to see a tornado. Here's a rain shaft. It's easy to recognize it for what it is. This one's tougher. It's the same rain shaft 10 minutes later. This one could fool you. If you're not sure, watch it over a period of time. The meteorologist who filmed this rain shaft watched it for 15 minutes until it finally disappeared. It is not a tornado. To conclude, here's a life cycle of a tornado as a spotter might see it. First, looking toward the southwest edge of the storm, a wall cloud. 30 minutes later, a damaging tornado is formed out of the wall cloud. 10 minutes after the frontal forms, the tornado has reached its maximum size. Tornado lifetimes last from less than a minute to over an hour. This one stays on the ground for another 15 minutes. Here we see it near the end of its life. It shrinks into the rope stage, yet it is still destructive. Even as we watch it, it levels a farmhouse hidden in the trees 2 miles away. We can't prevent tornado devastation, but with early warnings, we can save lives.